everybody. In this video, let us discuss about the next chapter, condensed matter physics. Okay. First, let us go for some basic fundamentals regarding the condensed matter physics. We can also call it as solid state physics. Now, this is the printed notes which I gave to my UG students. So first I'm explaining that particular basics which we covered in our UG, and then let us go for the PG syllabus. So first let us know what is crystalline nature of matter. Now see these two diagrams. In these diagrams, the atoms are arranged in a regular fashion. In this diagram, the atoms are arranged in irregular fashion. Now, this we call it as crystal. This we call it as amorphous solid. So, amorphous solid means that particular substance in which atoms are irregularly arranged. No particular arrangement will be there. There will be a random arrangement of atoms. Now, this we call it as crystal solid. The particular solid or a substance in which atoms are arranged in a regular manner. Okay. Now, first let us go for some small definitions between this crystalline nature and amorphous nature. Crystalline nature, solids have regular arrangement of particles. These have different physical properties in different directions, so they are called as anisotropic. So, crystalline nature are anisotropic. Cooling curve has breaks which corresponds to process of crystallization. All bonds are equally strong due to their symmetry, and melting point is very sharp. Now, in case of amorphous solids, solids have completely random arrangement of the particles. They have physical properties same in all directions, so they are called as isotropics. Cooling curve is smooth, no breaks. Okay. All bonds are not equally strong, and melting point is not so sharp. Now, this is a difference between the crystalline and amorphous solids. Now, next, let us go for some small definitions. First, let us take what is lattice. Now, here I am drawing lattice means this one, the periodic arrangement of atoms. We call it as lattice, the periodic arrangement of atoms. Now, next, basis. Basis means certain atom or molecules are attached to this lattice. Certain atoms or molecules which are arranged to this lattice, that we call it as basis. Okay. Now, next, unit cell. Unit cell means the volume of a solid, the particular volume of that crystalline solid through which entire crystal is constructed by translation, repetition in 3 dimension. Now, for example, if I take a unit cell in such a shape, crystal means repetition of this particular unit cell. Okay, if in dot, if I take, now repetition in translation motion like this, 3-dimensionally. Repetition in translation motion 3-dimensionally. So, the volume of the particular solid from which the entire crystal is constructed, if I take the volume of this particular solid, this point, if this point repeats 3-dimensionally in translatory, Okay. Translatory means in such a way in a straight path. So translatory three-dimensional motion. Then a crystal is formed that we call it as unit cell. So the volume of the solid from which the entire crystal may be constructed by translation of a repetition of a three dimension. Now coordination number. The number of equidistant neighbor. Now the neighbor for this in such a way. The number of equidistant neighbor to this particular, there will be neighbors surrounding, no, the atoms around it, no, all that particular atoms we call it as coordination number. Crystal structure. Now crystal structure means lattice plus basis. Basis means atoms or molecules attached to the lattice points. This each we call it as, here we arranged the atoms in a periodic manner, no. Now this each one we call it as lattice point. Atoms or molecules attached to it we call basis. So lattice plus basis we get crystal structure. Now next, yeah, fine. Solid. Now, solid is one distinguished for constancy of form and volume, which has, in a simple manner, I can say, which has the perfect dimensions and the volume. That we call it as solid. Right? Unit cell means, now only I said, the particular volume of the solid through which entire crystal is constructed by translation repetition in three dimension. Crystal lattice means we can say the array of points related to lattice translation. Here we write the translation operator as UA plus VB plus WC, where U, V, W we call integers and A, B, C translation vectors. Now next one, the axes ABC are primitive for minimum cell volume, A dot B cross C for which the crystal structure can be constructed from the lattice translation operator. Now next, the set of points defined by the integral linear combination of primitive translation is called Bravais lattices. What are Bravais lattices? A set of points which come due to the combination of primitive translation vectors. In next topic, let us see what are Bravais lattices. Right? This is nothing but a set of points which comes by the combination of primitive translation vectors. T equal to UA plus VB plus WC we call Bravais lattices. There are 5 Bravais lattices in 2-dimensional and 14 in 3-dimensional. 5 Bravais lattices are in 2-dimensional and 14 Bravais lattices in 3-dimensional. Right? Now next, the total number of crystallographic symmetry elements. Let us write as, so elements of symmetry. Okay. Now here he is talking about the total number of crystallographic symmetry elements of a cubic crystal are given by center of symmetry. 1 we will have. In that straight planes, diagonal planes, 3, 6. 4, 9 planes are there. Tetrad planes, triad axis, dyad axis. Tetrad axis 3, triad 4, dyad 6. 2 axes, 3 axes, 4 axes. Diagonal plane. Now only I draw the crystal. No, this is the diagonal. This is the diagonal planes. Okay, straight planes. Now straight planes means I will show you. Straight planes, diagonal planes. Okay, so diagonal planes, 3 for crystallographic symmetry elements of cubic center. Diagonal planes 6, total planes 9 planes. tetrad axes. These are planes. Now these are axes. Tetrad axes 3, triad axes 4, dyad axes 6. Totally 13 axes, 9 planes, 1 center of symmetry will be present in crystallographic symmetric elements of a cubic system. Right? Now the directions are denoted by U, V, W. And Miller indices, let us discuss about it in detail, HKL. Okay. Now next, a small box. Before going for this box, let us go for first types of crystals. Okay. Or simply 7 crystal structure. First comes to be cubic crystal. Okay. Here the lengths are equal, angles are equal. Length A equal to B equal to C. Angles alpha equal to beta equal to gamma. That is equal to 90 degrees. Examples are sodium chloride NaCl, calcium fluoride CaF2, diamond, etc. Second crystal is tetragonal crystal. So now here A is equal to B but not equal to C. But alpha equal to beta equal to gamma equal to 90 degrees. Now examples are nickel sulfate, NiSO4, SnO2, etc. Next comes to be orthorhombic crystal. Here A not equal to B not equal to C. But alpha equal to beta equal to gamma equal to 90 degrees. Now examples of orthorhombic crystal are potassium nitrate, barium sulfate, etc. Right? Now next comes to be monoclinic crystal. Here A not equal to B not equal to C, and at the same time alpha, beta, gamma not equal to 90 other than 90 angle. Example, sodium sulfate, ferrous sulfate, etc. Next, triclinic crystal. Here A not equal to B not equal to C, lengths, and axes is also alpha not equal to angles, alpha not equal to beta not equal to gamma. Examples, copper sulfate, potassium dichromate, etc. Next, rhombohedral crystal. Here, now again A equal to B equal to C, alpha equal to beta equal to gamma but other than 90 degrees. Example, calcium sulfate, quartz, calcite, etc. Next, hexagonal crystal. Here A equal to B but not equal to C. Alpha equal to beta equal to 90 degrees angles and gamma is 120 degrees. Silicon dioxide, silver iodide, etc. are examples of this hexagonal crystal. So totally 7 crystal systems are there. So what are there? 7 crystal systems: cubic, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, hexagonal. Now number of lattice system here 3, for tetragonal 2, for orthorhombic 4, for monoclinic 2, for triclinic 1, for trigonal 1, for hexagonal 1. And characteristic symmetry elements. For cubic 4, threefold rotation axes will be there. For tetragonal 4-fold rotation inversion axis. For orthorhombic 3 mutually perpendicular 2-fold rotation axis will be there. For monoclinic 1 2-fold rotation axis. For triclinic none. For trigonal 1 3-fold rotation axis. For hexagonal 1 6-fold rotation axis. Now lattice symbol. Here P for primitive, I for body centered, C for base centered, F for face centered. Let us discuss these also in detail. So first, cubic has primitive, that is simple cube. Body centered, or shall I write simple cube, body centered, okay, and F is face centered cubic. Now here simple cube, body centered cubic, tetragonal. Now here all 4 lattice symbols we are writing: simple cube, body centered cubic, face centered cubic, and C is base centered cubic. Now here monoclinic, simple cube and base centered. Triclinic, simple cube, tetragonal, simple cube, hexagonal, simple cube. Now unit characteristics, now only we read cubic, A equal to B equal to C, alpha equal to beta equal to gamma equal to 90. In a similar manner, now only we completed. Now next, Bravais lattices. Bravais lattices means in 1848, Bravais showed that there are 14 independent ways of arranging these 7 crystal system. Let us see the 14 possible ways. This only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 14 possible ways of arranging 7 crystal system, we call it as Bravais lattices. Right? Now here, after this, let us discuss about the simple cube, face center, body center. Or here in this only first I will discuss. First in cubic crystal, 3 we are having primitive. That we call simple cube. Next, face centered, body centered. Simple cube means what? So, I took a unit cell in such a way. Now see, at each corner, one lattice point is there. 1, 2, 3, 4, 5, 6, 7, 8. So, at each of 8 corners, there is one lattice point. So, total number of lattice points in simple cube, 8. Now, next, face centered. Now, here, face centered means, now one at each corner, one lattice point will be there. Totally 8 lattice points plus 6 faces. 1, 2, 3, 4, 5, 6. At each face again one lattice point will be there. So 8 plus 6, 14. Total lattice points in face centered is 14. What is face centered cubic? At 8 corners we will have 8 lattice points. Each corner one lattice point, 8. Plus at 6 faces again we have 6 lattice points. We call it as face centered. Now next, body centered. At the center of body, one lattice point will be there. As usual, at 8 corners, 8 lattice points are there. 8 plus 1, total lattice points 9. Now 3 types. Now tetragonal, only 2 types. Body centered, simple cube. Now orthorhombic can be arranged as simple cube, body center, face center, base center. Base center means, as usual, at each corner, at 8 corners, 8 corners are there. No, 1, 2, 3, 4, 5, 6, 7, 8. One lattice point. Plus at bases, 1, 2 bases. 1 lattice point. 8 plus 2, 10 lattice points will be there in base centered cubic. Now next, this can be arranged in 4 types. Now monoclinic is arranged in 2 types. One is simple cube, base centered. Now triclinic, only 1 type, simple cube. Rhombohedral, simple cube, hexagonal, simple cube. Right? So in such a way, if we count, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. The 14 independent ways of arranging 7 crystal system. In hexagonal system, how many lattice points are there? You see 1, 2, 3, 4, 5, 6. 6 plus 6, 12. 12 lattice points are there in a hexagonal system. Okay. Now next. Now we completed the crystal structure, no? Now let us go for their coordination. Crystal structure. Simple cube, body center, face center, we are talking. Coordination number 6. Coordination number means nearest neighbors surrounding that particular lattice point. How many neighbors are there? 6. For body center, 8. For face center, 12. Atomic radii, A by 2. BCC, root 3 by 4A. FCC, root 2 by 4A. Number of atoms per unit cell, here 1. Body centered, 2. Face centered, 4. And spacing of sets, that is 1 by D1 is to 1 by D2 is equal to 1 by D3. Set of planes. 1 is to root 2 is to root 3. 1 is to 1 by root 2 is to 1 root 3. 1 is to root 2 is to root 3 by 2 for face center. Density packing for simple cube pi by 6. For body center root 3 by 8 into pi. For face center root 2 by 6 into pi. Right? Now next, the relation between the density of crystal material lattice constant. The formula for lattice constant. MAN by NA rho and whole to the power of 1 by 3. Where Ma atomic weight, rho density, Na Avogadro number, N number of molecules per unit cell. Okay, per unit cell. Now next, let us go into details regarding some elements of symmetry. Symmetry means same, right? Here symmetry means nothing but same. It explains the elements of symmetry. It explains about symmetry of crystals. The three main elements of symmetry are axis of symmetry, plane of symmetry, center of symmetry. First, axis of symmetry. This symmetry refers to the axis around which if we think axis around which the crystal rotate around that particular axis. Now this crystal occupies two or more identical positions during its rotation through 360. Then such axis of rotation we call axis of symmetry. Okay. Now here we consider the rotation y dash about 90 degrees. Now it is a fourfold axis of symmetry. So 90 degrees, in this case cube has 4 identical positions. So we call fourfold symmetry. Now next, plane of symmetry. Now see, the planes which cut the crystal into two halves. Either it may be a diagonal cut. Okay. Now figure A shows the parallel cut. Parallel to top and bottom. Here we cutted the plane, the shaded part. It is parallel to top and bottom. And now dividing into two mirror image halves. We see it as mirror image halves. Now diagram B shows diagonal cut. 6 such diagonal planes are possible. Okay. 6 such diagonal planes are possible. So for cubic system there are 9 planes of symmetry. Now center of symmetry. This refers to that particular point through which a line is drawn. From any lattice point, a line is drawn. From any lattice point. Now the crystal through this point, when produced equal distance on opposite sides, meets the same identical point. If you produce this, it goes and meets the same identical point. Or simply we can say plane passing through center of gravity of cube. Plane passing through center of gravity of cube is called center of symmetry. Right? Now next, let us go for in detail about the structures. Simple cube, one of the unit cell we took. Now here, this is 1/8 of atom, corner atom. The unit cell, lattice points per unit cell. At each and every point, what we are having? The one lattice point at each 8 corners. Okay, at each 8 corners, we are having one lattice point. Each lattice point form simple cube. Okay, again each, now I am drawing here. At 8 corners, 8 lattice points are there. Again each this particular lattice point is a member surrounding 8 other cells. This repetition only we call crystal. So again each lattice point surrounds, each lattice point surrounds with 8 cells. So now the share of each lattice point will be 1 by 8. This is surrounded again with 8 lattice points, I said no. So the share of one lattice point will be 1 by 8. So number of lattice points 1 by 8. and into 8 why I wrote at each corner there are one lattice point, 8 lattice points into the share of each lattice point 1 by 8, so that is equal to 1. So only one lattice point per unit cell is present in this simple cube. Atomic radius, now 2 are equal to a is the distance between the two lattice points, so r equal to a by 2. Now next, packing fraction, definition, volume of all atoms in unit cell by volume of unit cell. This can be written as number of spheres into volume of each sphere by volume of each cell. So number of spheres only one we are taking, volume 4 by 3 pi r cube, and volume length into breadth into height a cube. On simplification, the packing fraction is 52%. Most important, you have to remember the packing fraction of simple cube, 52%. The coordination number of a simple cube. Now what we said, 6. Okay, the coordination number of simple cube, 6. Most important, atomic radii, a by 2. Density packing, pi by 6. Now body centered. As usual, at 8 corners, 8 lattice points, and each lattice point is surrounded with 8 surrounding cells. So the share of each is 1 by 8. 8 into 1 by 8, 1 lattice point at corners. But body centered, no? Right? So at the center of body, 1 lattice point is there, no? Okay? Total number of body centered lattice is 1. 1 lattice point is there, no? So 1 plus 1, total number of lattice cells 2. Now atomic radius 60 4r by root 3 atomic radius, and packing fraction 68%. Now next, coordination number 8. Right? Face centered crystal structure. Now, as usual, share 1 by 8 into 8. 1 lattice point we will get at the corner. Now, face centered. How many faces we are having? 6 faces. Right? Now, 6 faces. Now, the total number of faces concerned is 6. Now, these 6 face lattice points are the member of 2 cells. So, the share becomes 1 by 2. So, around this face centered, again, it is the share of 2 particular cells. So, the share of each cell, 1 by 2. 6 into 1 by 2, 3. 3 plus 1, 4. Number of lattice points, 4. Now, atomic radius, 4r by root 2. Packing fraction, 74. For simple cube, what is the packing fraction? 68. Okay. For body centered, it is 52. For face centered, it is 74. Most important bits. Now coordination number 12. Now coordination number for simple cube is 6. Body centered 8. Face centered 12. Okay. Now next, let us move to the Miller indices. Miller indices means another most important bit. A set of 3 integers. Okay. Which used to explain the orientation of crystal planes. What is the use of Miller indices? Which describes the orientation of crystal planes. The crystal lattice is regarded as made up of equidistant parallel lines in such a way. Okay, we call it as lattice planes. The planes passing through the lattice points we call parallel to each other, we call lattice planes. Lattice planes can be chosen in any way, which now I showed in the diagram. Now, to know about the Miller indices, I took one particular face, A, B, C. A intersecting X, B, Y, C, Z. Now, first, I took OA equal to P, AB equal to OB equal to Q, OC is equal to R. Reciprocals I took 1 by P is to 1 by Q is equal to 1 by R. Then LCM, then we will get the Miller indices. Example I took 2, 3, 4, PQR. 1 by 2, 1 by 3, 1 by 4. Now LCM is 12. So by dividing we get 6, 4, 3. Right? 1 by 2 plus 1 by 3 plus 1 by 4. LCM 12. 2 6 are 12. So 1 6 are 6. Now 3 4s are 12. 1 4s are 4. 4 3s are 12. 1 3s are 3. So 6 4 3 is the Miller indices. Now if we give such a plane set, then the Miller indices, now see here, shaded part, it is intersecting Y, not Z or Y. So now here Miller indices directly I am saying how we will write. It is intersecting Y, no? This is 0, 1, 0. This is intersecting X, no? 1, 0, 0. This is intersecting Y and X. So 1, 1, 0. Now next this is intersecting X, Y, Z. So 1, 1, 1. Miller indices. Now this is intersecting Z only. So 0, 0, 1. Right? So next, let us discuss some formulas. So relation between the density of crystal material and lattice constant we already completed. Again I am saying the lattice constant A equal to MAN by NA rho whole to the power of 1 by 3, where Ma is the atomic weight, rho is the density, Na Avogadro number, N number of molecules per unit cell. Now the next formula, bonding force F1 between the atoms. F of R equal to A by R to the power of M minus B by R to the power of N. Okay, where N is greater than M. R is the center to center spacing. Okay, A, B, M, N are the constants, characteristics of molecules. Now next, the spacing R naught is equal to B by A whole to the power of 1 by N minus M. Cohesive energy U of R equal to minus A by R to the power of M plus B by R to the power of N. U of R exhibits a minimum force for R equal to R naught when du by dr at the R equal to R naught equal to 0. Now U minimum is equal to minus A by R naught M. R naught the spacing between the molecules, A lattice constant, Mn the characteristics constants of the molecules, 1 minus M by N. The lattice energy, the most important formula, minus A Madelung constant we will call. A E square Na by 4 pi epsilon naught R naught N minus 1 by N. Okay. Now here lattice energy means the energy released in the process when constituent ions are placed in their respective positions in crystal lattice. When we keep the ions in their position, an energy is released. That energy we call it as lattice energy. Okay. Now next, here, next, the total energy. Okay. Total energy due to all ions in linear array minus E square by 4 pi epsilon naught R naught 2 log 2. 2 log 2 is the Madelung constant per molecule of ionic solid. The total Coulomb energy, most important formula, U equal to minus Na E square by A 4 pi epsilon naught R naught. A Madelung constant, Avogadro number Na, E is the charge of that particular charged particle. Okay. Epsilon naught permittivity of the medium, R naught the spacing. Now next, before going for this types of bonds, once let us see what is this Madelung constant value. Okay. Here, we took NaCl crystal. Okay. So now the attractive potential energy between Na plus ion 6Cl minus ions at a distance R0. Here we are imagining two ions of opposite charges. They are allowed to come closer and closer due to attractive force. But due to electron clouds, that there will be repulsive force between them, right? When they approach closer to each other, attractive force. But due to the electron cloud, we find repulsive force between them. We are considering a single Na plus ion. Okay, these solid dots are Na plus and circles are Cl minus. So Na plus ion which is situated in NaCl lattice. Now consider single Na plus. Attractive potential energy between Na plus ion and 6Cl minus ions surrounding it are minus 6 E square by 4 pi epsilon naught R naught. U1 equal to attractive potential energy between Na plus and 8Cl minus ions at a distance root 3 R naught minus 8 E square by 4 pi epsilon naught in place of R naught root 3 R naught. Now repulsive force between Na plus and 12 other Na plus ions at a distance root 2 R naught. So that is 12 E square by 4 pi epsilon naught root 2 R naught. Similarly, the repulsive force between Na plus and 6 Na plus ions at a distance 2 R naught. 6 E square by 4 pi epsilon naught 2 R naught. Now, here we are summing all this. Now, this constant value E square by 4 pi epsilon naught R naught will be common. So, remaining minus 6 minus 8 by root 3 plus so on we will get. The constant value is minus 1.7475 E square by 4 pi epsilon naught R naught. Now, if we consider Avogadro number or for 1 mole of solid lattice energy, we write the same equation as minus 1.7475 N, where N is the Avogadro number, E square by 4 pi epsilon naught R naught. Now here, the constant which multiplies the factor minus E square by R naught. What is the constant which is multiplying minus E square by R naught? 1.7475 N. We call it as Madelung constant or 1.7456, the exact value N. So this is Madelung constant which is multiplied to minus E square by R naught. And now let us move for the bondings. Okay. So types of bonds. Now here we know that there are 4 types of bonds. Okay. The same thing I wrote here. Ionic crystals. Ionic means this is formed due to electrostatic force of attraction between oppositely charged ions such as Na plus Cl minus becomes NaCl. So, the ionic bond is an electrostatic force of attraction between two oppositely charged ions formed by the process of electron transfer. Sodium loses the electron and becomes positively charged. Chlorine gains the electron and becomes negatively charged. Now, electronic configuration, atomic number 11. So, 1s2, 2s2, 2b6, 3s1. In this, the valency electron is 1. So, sodium loses that 1 and chlorine gains that 1. Okay. Now, chlorine is 17, 1s2, 2s2, 2b6, 3s2, 3p5. Now, after gaining, it becomes 3p6. Right. Now, characteristics are, the crystals are in structure. They are crystals in structure. They crystallize in relatively closed packed structure. They are rigid. Now, due to electrostatic binding forces, they have high melting and boiling points. They are highly soluble in solvents like water, liquid ammonia, and insoluble in nonpolar solvents. Now, this is about ionic crystals. Now, next characteristic, they are directionless. Okay. They are generally non-conductors of electricity, but their melts and solutions conduct electricity. Next one, molecular crystals. All atoms, molecules, including those of inert gas, exhibit one kind of weak attraction for one another. The kind of attraction force is a short range force, and this short range force we call it as van der Waals force. So a molecular bond or van der Waals bond is formed due to van der Waals forces of attraction. The crystal so formed is called molecular crystal. Now, characteristics: in absence of ionic or metallic bonding, this bonding alone is responsible for condensation of gases into liquids and freezing of liquids into solids. Now, friction, viscosity are due to this bonding only. They have low melting points, they are good insulators, they are transparent to light, they have little mechanical strength. Now, the next comes is covalent bonds. These covalent bonds are due to sharing of atoms. Okay, do similar or dissimilar atoms we take, they achieve stability by sharing the valency electrons between themselves. Here, electrons are not transferred, but they are shared in such a way. Now, germanium is there. For example, I am saying, okay, germanium substance I took, which consists of number of germanium atoms, right? Number of germanium atoms. Germanium valency number is 4. How many valency electrons are there? 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, 1, 2, 3, 4. So, 4 valency electrons are present in the germanium. Atomic number is 32 and number of valency electrons 4. So, now in order to get the stability, they share the electrons in such a way. Right? A bond is formed due to sharing of electrons. Valency electrons. Sharing of valency electron. So, such a kind of bonding we call it as covalent bonding. Now, the characteristics: they are hard, brittle metals. They have high melting and boiling points. They dissolve in non-polar solvents like benzene, etc. Basically, they are insulators because no electrons are available for conduction. They are insulators. Some are semiconductors like germanium. Okay, maximum are insulators, some are semiconductors like germanium. Semiconductor means whose resistivity lies between a good conductor and a non-conductor or insulator. Now, these are transparent to long wavelength but opaque to short wavelength. Now, the last crystal bonding type is metallic crystals. Now, metallic crystals, in every metal, valency electrons are mobile because they are not tightly bonded to mother nucleus. They are loosely bonded to mother nucleus. If you give somewhat thermal energy to them, they come out from the attraction of mother nucleus and move freely in the crystal or a substance. So they are mobile and not bounded to any particular atom. These free and mobile electrons form electron gas. There exists an electrostatic force of attraction between this electron gas and positive ion core. Positive ion core means now germanium. This circle which I drawed, we call it as ion core. This ion core, 32 is the atomic number. No, it consists of 28 innermost electrons of germanium. This circle means 28 innermost electrons of germanium. To that, 29, 30, 31, 32. 4 valency electrons will be attached loosely, not tightly, to this ion core. Now, how the metallic crystals are formed? Here, there exists an electrostatic force of attraction between this electron gas. Electron gas means that particular formed due to the free electrons in the substance and this positive ion core. A metallic bond is formed when force of attraction between positive metal ions, electron gas, exceeds the mutual repulsion of electron in that gas. Now, characteristics: crystalline in structure, high thermal conductivity, high electrical conductivity, moderate to high melting temperatures, opaque to all electromagnetic radiations from very low frequency to middle ultraviolet, where they become transparent. They have high optical reflection and absorption coefficient. Now, this is about the types of bondings. So, in this video, we discussed about some definitions related to unit cell, crystal lattice, Bravais lattices, some then crystal structures, their atomic radii, 7 crystal systems, some formulas, and then bonding, ionic bonding, Miller indices, elements of symmetry, face centered, body centered, and simple cube base centered. Okay. So now these are the some important information related to the SSP, solid state physics. So thank you for watching my channel. Stay with my channel to receive the more important points related to condensed matter, which is useful for TS set. Thank you for watching. Yours, Reshma Physics. Please subscribe, share it. Thank you.